Okay, I'm going to go ahead and start recording, even though we're kind of waiting for some more people maybe to come. So, um, yeah, welcome back from the break, everybody. Yeah, today, well, we're going to continue on. I'm not going to say too much about the test one evaluation unless some people that are here have some questions on it. So everybody did fine on that. I didn't have anybody except for maybe one or two people that really had any problems on the test one. But I did put back an example solution on that. I think maybe the only thing I'll mention about that, just in case people are wondering, if you want to go back and review on the test one, it sort of be a good idea. There were multiple versions of each of the questions, so you can also get additional practice if you're interested. You can go in and look at the other versions of the questions that you didn't get. Maybe think about how you would have answered those. So really, as I was hoping, the last two questions, which were on doing a linear regression and a logistic regression, I think almost had 100% on almost everybody, which was great. So I didn't give a lot of feedback on these. I mostly went in there, checked that you did do the question that was given to you among the ones that I had up there, and I spot checked mostly that, for example, on the first one that you had we're using a function, it was vectorized, and for the second and third one I was mostly checking that you got the expected fit. So if you generated the data as was shown using the random seed, you should have gotten exactly the same fit on the parameters and the exact same results in terms of whatever your mean squared error was or whatever your accuracy was on the logistic regression. Okay, but anyway, that's up there. I don't think I'll review any of the questions there, but let me know if anybody has any questions looking through that. So the second test will probably be a similar format at least. I'll do it in the same way. So our final test will be kind of comprehensive. We'll give it at the end of the semester, either during the last week of classes or maybe during finals week, depending on how things go out. But it'll be online through MyLeo Online. There'll probably be 2 or 3 questions through the MyLeo Online quiz function, and you'll have to do it in a notebook again and just upload the notebook when you're done. So everybody should be familiar with the format then once we get to the end of the class. So also thinking about stuff for the class, I just thought I'd remind people about the project. So I had 1 or 2 questions the last week or two, people working on the class project. So I probably am going to have one of my things that I'll probably check when I'm checking this is that you were showing that you were working on it during the semester. So if you haven't been looking at it and making commits yet very much, I really would encourage you to start at least like once a week, going in there, doing some work on it, making a commit. That's kind of a minimum. I hope most people do more than once or twice a week, are doing something on the project, adding a notebook or modifying it or, that kind of stuff. And just keeping that in mind, trying to make good progress on that. So I'll keep reminding people about that. I'm probably going to ask people to do a little bit of a write-up as well. I don't have anything in there about that yet, so just keep that in mind. Like maybe near the end, I'll ask you maybe a README file, so in like a Markdown file in your project, to give sort of like a final project report. So give a brief description of your introduction, like your methods, and then like describe your results like in a paragraph or 2 in each of those. So I won't ask for like a big, a big formal written report, but I will maybe ask for a little bit of a write-up. So it's not all just a notebook or a couple of notebooks. the things that I had asked, since I'm talking about this a little bit here, I had a question about, I guess, about the project structure, really. Right. So, I mean, this description down here really isn't part of the project. In fact, this was kind of copy pasted from some old stuff. But I guess I would like people to, use the directory structure of a project, correctly. So use relative path names, and you probably shouldn't have like a lectures subdirectory, but you should probably call it like I think I did change it to like a notebooks subdirectory. So I might, you'll have to add these things in yourself. So again, this is kind of open-ended. So it's not that I'm requiring you to have any particular structure or anything, but I would like you to at least use the directories that make sense for the stuff that you do. So that might mean at least like a data subdirectory and maybe a notebooks subdirectory or something like that, where you have a couple of IPython notebooks and your data in a data subdirectory. You can certainly do more. So the person that was asking me was I looked like they'd been looking at this thing in the README here. So if you do end up creating multiple notebooks, which I do think is not unjustified for this project, because I think that maybe a good idea to shoot for you might want to at least have like a notebook where you do some data exploration, then another notebook where you actually do your cleaning, where you actually build your workflow for your data set, so that you're going to get it cleaned up in a format, and then maybe one or a couple of notebooks where you actually try and fit some models to it. So where you're kind of doing the actual thing that's sort of the point of this course of trying to model the data. So trying to get a good fit for the data that does well at predicting whether you're doing a classification or a regression task for it. So if you kind of follow that suggestion, you ought to have at least maybe 2 or 3 separate notebooks. So once you have a couple of notebooks, you might find that there's common code. So best practice, instead of copying that code multiple times, so copying a cell from one notebook and putting it in another one, you might want to think about taking that out and putting it into a function, into like a source subdirectory, and then just importing your function, right? So then you just have one copy of like your code that does the full pipeline to clean the data, or whatever other function. So you might find that you visualize like maybe you're plotting learning curves or something simpler. So you might have a function that creates a visualization that you do multiple times in your notebook, that kind of stuff. So that's usually the purpose of the source subdirectory in this kind of a project, is you'll have common code that's put into like a file, or like a file that's meant to be a module that you import, and then you reuse that in multiple places. The others you may or may not have. So, since I might ask you to do a little bit of a write-up, but I probably won't, if you were going to make a document where you took your results and you created figures and stuff, you might want to have the results of creating figures that are going to be in your write-up would be in a figure subdirectory, and then you can include that in your markdown or your document that you create. That's So just to wrap up on this, I think that you should probably have a couple of things. You don't have to have a lot. I think most people probably should at least have like a data subdirectory with a few data files in there, assuming that you've got like a CSV file or something that was small enough that you could put in your project, and like a notebooks file with a couple of notebooks. And you might use some of these other things. So, if you get into it, you might have extract some things out, have a source subdirectory. You might add it into your workflow so that you create some figures and things that you use in like a write-up in a figure subdirectory and so on. But so I'll leave it at that for now. But I have some people have been asking me questions about that. So if you're listening to me talking about the class project and you haven't been doing much work on it, keep it in mind. Keep trying to make progress on it regularly. So, the same time that you're working on the assignments for the class, once you're kind of done with those, you might want to also go back and make a little bit of progress on your class projects and things. So. And another note before I get into stuff here, I did kind of switch around. I am going to talk about the support vector machine stuff this week. And then next week is kind of a little bit of just a grab bag of a couple of other small methods. So I'll talk about some KNN and some other stuff. So I'd had those the other way around previously in this class. I put it this way because I also did post the assignment for support vector machine. So our assignment 4 should be visible. Let me check that here real quickly. But it should be, you should be able to click on it and accept it now. In our MyLeo Online, yeah, so I'll go ahead and accept it here. Assignment 4 really is on support vector machine, so it doesn't have any questions about k-nearest neighbors or naive Bayes, so we'll mostly just talk about that next week, but your assignment will all be on creating some support vector machine classifiers and using and also a little bit about some kernel stuff. So that'll be the stuff that I'll mostly talk about today and this week. Just give some background, make certain everybody knows what to do for the assignment 4, and we'll continue talking about the assignment next week as well as talk a little bit about these other things, the KNN and naive Bayes. Yeah, so I also just so I'm thinking about that. I didn't renumber the things in the notebook, so I probably should have. I forgot to do that. So anyway, I am looking at the linear support vector machine stuff here on this lecture today, and Thursday we'll probably continue looking at that. As well as I'll remind people also about if you haven't been using the Dr. Ng's lectures, again, I think his treatment of the support vector machines is really good. So the one labeled lecture 7. Hopefully I fixed all these links too. Let me double check this link here. So yeah, I think all those links to the videos are hopefully correct as well. So, but yeah, my plan is I'll go ahead and cover the linear support vector machine, and maybe I'll also use some of his stuff where he discussed in a little bit more detail the modifications to the fitness function that we need for support vector machines. So, all right. Okay, so with that, so I'm going to go ahead and at this point start with talking about support vector machines. Okay, so let's look at go through the lecture notebook. So the one labeled Unit 10. So this is actually our Unit 9 now for this semester here. This is material mostly directly from our textbook, so from Chapter 5 of our textbook on support vector machines. Yeah. So yeah, we're kind of past the halfway point of the course at this point here. So to this point in the course, we've only been talking about supervised learning methods. We talked about the two major things. So we've done a lot of examples of doing regression problems and doing classification problems. But we mostly haven't looked too much at the details of how machine learning models work, except that we looked at in a bit of detail linear regression and logistic regression. Okay, so for the next couple of weeks, we're going to be looking at each week at one or two different machine learning models or mechanisms that do supervised learning. Okay, so we'll look at support vector machines, naive Bayes and KNN real quickly, but then we'll look at ensembles and decision trees and some other stuff. And then later on in the course, we'll jump to unsupervised learning for the last 2 or 3 weeks. Okay? So so a summary of that is for the next couple of weeks, we're sticking with supervised learning, but we're going to start looking at more powerful, so more state-of-the-art machine learning methods, ones that will work well even on more complex data and data sets. Okay, so support vector machines that we're looking at this week. At one time they were really hot. They were the go-to thing that people would turn to if they needed to, if they had a kind of a tough data set. And they can still work pretty well. There's certain there's certain contexts where they'll be better than others. Nowadays, mostly neural networks and deep neural networks tend to be the most powerful mechanism. So for the toughest problems, you might have to go to using like a deep neural network. But still, ensembles and support vector machines can work very well for certain data sets. Okay? So we'll start by looking at the linear version of support vector machine classification. Okay? So I think I've touched on this in the past, the idea of data sets being linearly separable, but I might not have explicitly kind of discussed it or defined it before. So if you're building, and let's just talk about classification. So you can use support vector machines for classification or for regression. So at the end of chapter 5, it talks a little bit real quickly about regression. But support vector machines make kind of the most sense when you're talking about a classification problem, because usually what we want to do is we want to create a decision boundary in order to separate and classify a set of data into one thing or another. And we'll stick with binary classification. So the first example from chapter 5, if you didn't read the textbook, we're going back and we're using the Irish data set we've used a couple times for examples here. Just using 2 different classes. So there's actually the Irish data set is actually a multi-class problem, but we'll stick to the versicolor and the setosa. So turn to a binary classification task. Okay. So something is linearly separable if you can, in this case, like if we're just looking at 2 features, if there's a line that we can draw that would completely separate one class on one side of the line and the other class on the other side of the line for binary classification. Okay, so that's simply what linear separability means. Okay, so usually only the simplest problems are linearly separable, right? But this makes a starting point for understanding more complex things that we want to do for classification tasks. Right? So if you just think of a problem that's linearly separable, like this, that's relatively simple. If it's linearly separable, it's often the case that it can be linearly separated in many different ways, right? There's an infinite number of lines we could draw that would actually linearly separate the versicolor and the setosa classes on this diagram here, right? It only shows 2. This figure is just directly from the textbook. Right? So when we did the logistic regression, which was really a classifier, we defined a fitness function. Now the fitness function, any line, if the data was linearly separable, any of these lines would actually get the same fitness because they would they would lead to a classifier that would perfectly predict the data, right? So you wouldn't get any difference in the lines if you were using no regularization, if I was just doing a simple logistic classifier, okay? But intuitively, so that's where the large margin comes from. And that's the most basic thing to understand about a support vector machine is it's a large margin classifier, Okay, that's in some textbooks you'll see that used as the name for it, or as an alternative name for it, as a large margin classifier. So intuitively, if data is linearly separable, some of these decision boundaries are much better than the others in terms of they would lead to better performance in generalizing the data, right? Because for these data, just looking at it visually, it's obvious that versicolor, if other ones that we haven't seen, are probably still going to be clustered around here, and Setosa's down here, right? So, if you pick a line like this one, it is probably not going to generalize well because it's going to incorrectly classify possibly some Setosas that are a little bit bigger on the petal width than some of the ones we've seen, or some versicolors are a little bit smaller on the petal width that we've seen. Right? Same for like this one that goes right to the edge of some others, but maybe for petal width being a little bit bigger or smaller than kind of what we had got for the data that we traded or trained our classifier with. Right? So anyway, that leads to this intuition that all things being equal, if we have data that's linearly separable and we want to define a classifier for it, we ought to pick the decision boundary that maximizes what's called the margin here. Right? So that will get the largest value, the largest distance between the closest values to the decision boundary. So this one here is presumably the visualization of the largest margin that we could get on this one. So these 2 points would have been the closest. This one for the Setosa and this one for the versicolor. And the margin then is the distance between those, right? I'll probably leave this for Thursday, but really that is the main thing. And if you do watch Dr. Ng's videos, he talks about the modification to the fitness function that we use for logistic regression to support the large margin. So really, it's just a modification to the shape of that piecewise function that we use. Okay? And maybe I'll talk about that more later on. But for now, it's good enough to understand that by tweaking the fitness functions like we've talked about before for the logistic regression, we can change it to be sensitive to actually try and also find the decision boundary that maximizes the margin, right? So, and that's what the modification to the fitness function for the support vector machine is doing, right? So for the basic logistic regression, all these lines would really give you the same cost. They would have equal minimal cost. But if we make the modifications to be sensitive to the margin for linearly separable data, this one would have the lowest cost among any of the other lines that would separate the data. And that's what the support vector machine, the linear support vector machine basically does. Okay? So from that point on, if you understand that, that gives you kind of an intuition of what we're doing with the support vector machine. So to understand, though, how it actually works in practice, we do have to add in some complexity. So, the very first thing is that, most data is not going to be it's not going to be so simple. We're not going to be able to easily linearly separate it. So can this idea still help us build a classifier even for data that's nonlinear or that's not completely linearly separable, even though a linear classifier might still work okay for the data set? So yeah, the first thing we can talk about when we're loosening things up is the difference between soft and hard margin classification. So there's a parameter called C, which is a type of regularization parameter. So remember back when we talked about regularization, we added in two different types for linear and logistic regression, the L1 and the L2 type. So for support vector machines, we can use this parameter C in order to, the way that I think about it is it's a constraint on how much, how many points basically it will allow to be in the margin or even on the wrong side of the decision boundary, so to be incorrectly classified. Right? So yeah, you have to kind of know which way it is. So when C is small, that actually gives more loose constraints. Right? So that'll actually lead to wider margins. Or another way to think of that is small values of C, or when C goes to 0, you're saying that the margin can be really big, and lots of stuff can be in the margin or even on the wrong side, right? So even if we have data that's not linearly separable, we can tweak the C. We can make it small or really small, and still use the same fitness function, even though the best line in that case will have some or many points that are on the wrong side or within or really close to the margin, right? So it will still try and, so the way I kind of think of it about it is it will still try and get the largest margin possible, but it will just ignore some points. So it'll say these points are just the wrong, being classified wrong, or they're just too close, so I'll just ignore them. I'll try to maximize for the other points that I'm not ignoring, right? So another way to think about that is for a small c is that it treats some points as just being outliers, as being too difficult to classify. So it kind of throws them away, and it tries to build the best model it can after ignoring points that might be outliers or might be not linearly separable, basically. You can go to the other extreme. So if you make C really high, you will try and force it to use a hard margin. So yeah, our textbook gives the definition of hard versus soft margin. So when C is high, it's going to try best it can to find a decision boundary that's linearly separable. Right? So in that case, another way to think about that is if you're thinking of these in terms of outliers, if I have like one point here that might be like an outlier, that was like a versicolor point, or maybe even like here or something. So in that case, I mean, if you're using a hard margin, this one here might be the optimal because this is still going to keep it linearly separable. But if you make C small, you soften up the margin, it might ignore these points because that might be an outlier, or that might be misclassified. That might have really been a setosa, even though it had come in being classified as a versicolor. So like, if we ignore that point, the best would be that, just kind of throwing that out, ignoring its effect on the margin here. So anyway, that's kind of how I conceptually think of the tuning of C here. The smaller it is, the more regularization we're going to use. So we'll allow it to ignore points that might be outliers or might be messing with the fit or might not be linearly separable in the first place. Or we can make C big and we'll force it to give us, if at all possible, find a linear decision, a boundary that does separate the training data completely, even though it might lead to poorer performance on generalized. Okay, so I should come back to that because that's one of the things that we do on the assignment 4. One of the first things we do is we'll fit some data and we'll try, I'll have you try different values of C to see the effect of softening or hardening up the margin in terms of performance on the data set. Okay. So in general, though, if we want to use a support vector machine, you'll be, if we're going to be using scikit-learn like we will for this class, you'll be familiar with the API is going to be the same as what we've been using so far. So if we create, I did skip over this. Support vector machines in particular can be very sensitive to the scaling of the features. So we've discussed this a little bit before, but it can be especially important for support vector machines to make certain that all features are on the same scale. So that's what we're doing here. So you typically would probably want to use a pipeline to first scale the features before you actually fit them to a support vector classifier. So yeah, that's all we're doing here. So we're just using a standard scaler, which will do the scale all of the data. So it has like a mean of 0 and a standard deviation of 1 before we fit it to our model. There is a linear support vector classifier. So we'll probably talk more about this on Thursday than today. I don't know if I want to get into it too much today, but the default, though, so if we look further on in this example here, there's just there's also an SVC, support vector classifier, in scikit-learn. So the default here is you can actually use what are known as kernels in order to build nonlinear classifiers. Okay? But one of the kernels, you can use a linear kernel for SVC. So this should be equivalent to that. So linear SVC is equivalent to doing just an SVC with a linear kernel in scikit-learn. I believe that's true. I don't know if there's any difference or not. So so I'll talk a little bit here about what nonlinear kernels are here, because that's also another thing that we do on the assignment 4. So the second half of the assignment 4, we're going to be exploring this kernel function here that support vector classifiers use. So here, though, we're still, in both cases, we're just using a linear classifier. So we're going to end up with a linear decision boundary. And in both cases, we're using a relatively small value of C here, right? So we're saying that the margin should be relatively soft here. So things close to 0 end up with soft margins. And we can see the result of this. So I can't remember. We changed a little bit from what we did on the example in the textbook. So we're using we're using the Irish data set still, but we're changing things into Virginica, not Virginica. So yeah, we used a different. I'm not certain why I changed it there. So the result here. So this is a good figure, though, maybe to look at a bit, right? So this was the result of fitting the linear classifier with a relatively large margin here. But we used the data here. So the circles were the not Virginica, and the squares were the Virginica. So you'll notice that the plot of the decision boundary has a lot of values that were in or violated the margin. So in this plot here, we make use of, maybe I'll talk a little bit about this because I can't remember, but in your assignment 4, you might want to use or reuse this function here or a similar one. So all this function is doing is it's expecting a model that's a support vector machine model. So one of the things for the support vector machine model is when you fit a support vector machine model in scikit-learn, you can actually get a list of these support vectors. So this is actually what we're using in order to visualize the margin around the decision boundary, and also, so this is really a list of those points that are violations that are inside of the margins, if I remember right. So anyway, we're doing something like that in here. Right. So I won't go through the details of that code, but the result for the data that we fit with, and we end up with a decision boundary here, and this was actually our margin. And a lot of values were inside or really kind of being ignored. So since our classifier was, this data here wasn't linearly separable. So you can see that, that there's some points here that are, that we really couldn't quite get a line through. Right? So it is interesting, if you haven't worked through this notebook, to try to see the effect of modifying C on these here. So I probably should have set this up to make it easier to do this, but let's say that we have our classifier right before we plot this here. So this should have been with 0.1, which was a relatively soft margin. So if we make that bigger, in this case, I mean this is still a pretty good decision. This data, the way that we separate it, wasn't linearly separable, but the best decision boundary that we can get is probably going to be something like that, right? Because of these points here. That we're not going to be able to separate with a linear decision boundary, but we want something probably with about that same location and that same slope there for our decision boundary. So, like if we try 1.0, in fact, so I guess it needs to be, I guess we have to pass in the linear SVC for this function to work here. Didn't realize that. Try that. I guess maybe I had to already have it fit before I called it. Probably, yeah, because I'd run some stuff below this. I probably need to just rerun everything above is probably my problem here. Let me just rerun everything above that, so. There we go. So with 1, yeah, we don't see much of a difference. Oh no, that was still 0.1. So if we change this to 1, I mean, we're still going to get a pretty similar decision boundary on this, but we'll see that it's making the margin harder, so the margin's going to end up being closer and closer. So if we make this even bigger, it gets down to there. So, so yeah, now that I'm thinking about that, so this isn't a real great illustration because in this case, a softer or hard margin is going to end up with a similar decision boundary because these points really aren't outliers. These points are just not completely linearly separable. So, but if we'd had some stuff where the points were problematic, more like outliers, that's where changing the margin will have a bigger effect in terms of where the decision boundary is and you know, how it might be oriented with respect to the data and that kind of stuff. So. But you can see, so with a really large, probably even larger, we can't get anything better in terms of, you know, since this data isn't linear separable, there's always going to be some points that are going to be violating the margin because they're going to end up on the wrong side of the decision boundary. So it doesn't matter how big you make C, in this case, for the nonlinear separable data, there's going to be some things that will be on the wrong side that will be violating our margin here. So always those points is the best we can do for our decision boundary. Okay. So yeah, we'll come back. I want to talk maybe some more details about that because that is one of the things that we do in the assignment. So we play around a little bit with the margin and that C parameter. But let's go ahead and begin talking about nonlinear support vector machine classification. So we've already kind of done this by hand. One of our whole assignments where we did the polynomial regression, what we were doing with that, we were doing regression instead of classification, but the data was nonlinear, and we were adding in polynomial features in order so we could fit a nonlinear model, a nonlinear regression line to our data. Okay? So you can do the same thing with classifiers as well, even though we didn't do those with like a classifier. But here, we're going to, the first example, again, I think this comes directly from chapter 5, in order to talk about what kernels do in support vector machines. But if you understood our assignment on doing polynomial regression, we can do that same trick. We can create polynomial features. So here, we're still using, we're using a different data set. So we're using this make moons, which creates data sets that are non-linearly separable. So the make moons data, the circles and the squares are what came out of the make moons here, this artificial data set here. So there's no line that's going to separate. We've got two features, x1 and 2, on this data set here. And we're not going to be able to get a good linear separation that will do well on classifying this data here. Right? So we can use that polynomial features like we did for regression in pretty much exactly the same way for classification. Here we're going to use it with a support vector classifier again that's doing a linear classifier, but because we are passing in the second and third degree polynomial features, so we're raising the two features to the second and third degree, plus we also have the combinations of these features, if you remember how this works. So we've got like x1 times x2 squared, and we've got x2 times x1 squared, and other combinations like that get created in this pipeline when we do the polynomial features of degree 3. So even though we're fitting a linear support vector classifier to it, we end up with a nonlinear decision boundary. Right? And you can see that, yeah, we're just reusing that. Might be lagging here. We're just reusing our function that we did before, but it was built so that we're using a contour plot in this function here in order to visualize the decision boundary. So we can, even if the decision boundary is not aligned, we will still visualize what the decision boundary ends up being for the support vector classifier that we build, as well as the margin by using those support vectors that we can get out of our fitted support vector machine here. Right. So you'll see here that we end up with a nonlinear decision boundary, even though we fit a linear support vector classifier. We were using a relatively high value of C, so this tried to be a relatively big, a relatively hard margin. So anything above 1 usually, I mean, it's going to be dependent on the data, but usually for me, 1 to 10 or so is where you're transitioning from being relatively soft when you're below 1 to relatively hard when you get to 10 or larger for your C here. So we end up with this boundary here. Right? And like we did before, I've encouraged people to play around with that. Like if we try and make it even harder, like make it 100 instead of 10, see what the result is. So you'll notice in this case, it does make quite a bit of a difference. It will make it more wiggly. Right? So another thing for higher C is if you're using less regularization. Right? So it will try its best to end up to get everything out of the margin that it can. So that might lead to overfitting when your C is too big here, because by trying to keep the violations as small as possible, we might actually be fitting to data that's outliers or really noisy. So overfitting the data in that case. So really, the kernel trick in support vector classifiers, so usually when you take a machine learning class, we will introduce what's known as the kernel trick here in the context of support vector machines. What the kernel does, it's the same thing as adding the polynomial features, the same kind of idea. So we're transforming the data into into a higher degree, so that even though we're fitting a decision boundary or a loss function that's linear, we're doing it on higher order data, so the actual decision boundary in the original features is going to be nonlinear now because of that transformation, right? And that's really kind of what a kernel does, although I will talk in more detail about this on Thursday. Right? So, but if you understand that conceptually, what we did to use the polynomial features for a regression problem, or what we just did for the classifier using the linear support vector classifier, that is the essence of the kernel trick. Okay? So some people, some students that are astute ask me, well, why do we usually talk about it for support vector machines? You can use that same trick like we just did here for any kind of machine learning model that is really making a linear decision, but you want to try and build a nonlinear model. The reason why it's especially useful for support vector machines is it's a mathematical trick, but there's a very efficient way. So it's a performance kind of thing. So you can actually do this transformation, this kernel transformation, in a way that that doesn't cost you any performance, right? So it can be expensive to calculate all of the polynomial combinations like we just did here. So the example that we just did by hand, this might not be feasible if I have data sets with billions of items with hundreds or thousands or millions of features. So even trying to put things up to degree 3, it would just, this is going to grow in time faster than the cube, which is not too bad, but still, this is going to take a lot of time to do that, and then also to fit the features there. All right. So, but you can actually get effectively the same idea if you do the transformation in a different way using these kernel functions. Okay? And I usually don't, we won't go into the real nitty-gritty details of that, but it is good to just understand on kind of high level. That's usually why people talk about this kernel trick for support vector machines. Is there's a mathematical trick that makes it very easy to do this with linear performance for support vectors. So yeah, we were using the linear kernel, but so instead of by hand doing the, getting the polynomial features, this should be pretty much the equivalent to what we were doing by hand. So this is going to be using a polynomial kernel, and you can even specify what degree of the polynomial kernel they want to use. So I'm not 100% sure. This isn't exactly using the kernel trick that we normally use with support vector machines. This is really doing pretty much the same thing that we just did by hand. Right? So instead of by hand calculating the degree 3 terms for our original 2 features, it will do it for us by using this polynomial kernel here. Right? So, so if I had set C to be 100, we should get pretty much about the same decision boundary, I think, here. If we compare those, let's check here. Like we got these 2 and that one. So maybe not exactly the same, but similar. Right? So that one didn't quite end up on the margin. But yeah, maybe if we tweak the coefficients a little bit here, we might be able to get it so we got the exact same decision boundary that we had before. So yeah, there's some more examples here, again showing using the polynomial kernel, but where we're changing C. So here we have a really soft margin, so very small C. So notice when you make the margin really soft, you end up with basically a linear classifier. So when it's close to 0, you're saying kind of you can make the margin as big as you want. So you end up with just the thing that goes through kind of the median location of the x1 and the x2. You end up with something pretty similar to just a linear a line for the decision boundary in this case here. So, yeah, and we'd already tried 100, so for that one, oh, well, no, we'd tried 10. So for 100, it's trying to completely get the margin, nothing in the margin here. So it will end up, it can end up maybe being overfit in that case if C is too high. Okay, so we've only got a few more minutes, but this is probably a good place to stop. So at this point, we can begin talking about the actual kernel trick a little bit, right? So I'm going to leave that for Thursday. We'll start that up on Thursday. I would encourage people, this stuff is a little bit, to get into the real nitty-gritty details of it, kind of hard to do in a class or two. So this would be a good thing, definitely, if you're interested in understanding the details of how the Gaussian kernels work, to look through Dr. Ng's lecture videos before Thursday. So he'll give you a better intuition of kind of how this works here. But I'll try and go over that a little bit, as well as a little bit more details of the assignment 4 that we have to do. Probably we'll start with that on Thursday. So. Okay. All right. Yep, that's it. Let me go ahead and end the recording.